Hi, this is Software Engineering with Mwila Nyurongo. Today, we will begin our deep dive into software architecture. This is a foundational topic for any computer science major, as it defines the high-level structure and organization of the systems you will build. In this module, we will explore several key themes: the fundamental concepts of coupling and cohesion, how to represent designs using UML package diagrams, and the various software architecture styles common in the industry. These styles include layered architectures, pipe and filter systems, object-oriented designs, implicit invocation models, and repositories. The building blocks of any architecture are its modules and the connectors between them. A hallmark of good architecture is that it minimizes coupling. Our goal is to ensure that modules do not need to know much about one another to interact. Low coupling is essential because it makes future changes to the system much easier to implement. While we desire low coupling between modules, we want high cohesion between them. Cohesion ensures that the contents of each module are strongly interrelated. High cohesion is a sign that the subcomponents of a module really do belong together, logically and functionally. When designing a system, we must consider Conway's law, which states that the structure of a software system reflects the structure of the organization that built it. Essentially, the communication patterns within your team will inevitably shape the technical architecture of your software. This leads us to the concept of social technical congruence. We can visualize this by looking at a map of people and a map of modules. By tracing the relationships between specific developers and the modules they work on, we can identify whether the social structure supports the technical requirements. If developer C is working on modules 1, 3, and 4, their communication with developers F and L must align with the dependencies between those modules. To be precise, a software architecture defines three things: the components of the software system, how those components utilize each other's functionality and data, and how control is managed across the system. A classic architecture example is the client-server model. In this style, servers provide specific services while clients request and use them. This style is effective at reducing coupling because servers do not need to know which or how many clients exist in the environment. Another common pattern is the three-layer architecture, typically consisting of a presentation layer, an application logic layer, and a storage layer. For instance, a presentation layer might use a Java AWT for application views, nowadays could be React, which then communicates with control objects in the application logic, eventually reaching a database management system in the storage layer. To represent these architectures, we use UML packages. These allow us to group UML elements together. These elements can be other packages, classes, or various models such as use cases, interaction diagrams, or state charts. But how do we decide how to decompose a system into packages? Common criteria include grouping by different owners, different applications, or clusters of classes with high cohesion, such as grouping course, instructor, and student together. Remember, each element in a UML model is owned by exactly one package. If the decomposition isn't immediately obvious, you can use an architectural pattern to help guide the process. Patterns provide a proven template for organizing components and their relationships. UML provides several ways to note packages. You can have a simple named package, a package listing, its contained classes, or a package that contains an entire class diagram. You can also represent nested packages or use qualified names to show ownership and hierarchy. As we move toward component-based design, we use these package structures to define clear interfaces. For example, a control package might contain a button and a checkbox that interact with an on-off interface, which is then implemented by specific hardware modules like a furnace heater or lighting light. Moving beyond our simple packages, we use component diagrams to show how high-level pieces of a system interact. In this modern context, you can think of these as microservices or discrete modules. For example, a till might send a sales message through a message queue, a standard way to decouple systems today, before it reaches a transaction processor within a sales server, which then communicates with an accounting driver. It is helpful to look at how these diagrams have evolved. In older versions of UML, component diagrams often distinguished between the application logic, infrastructure, and the underlying database. Notice how the seminar management application relies on various data access points that eventually point back to the university database. In the more modern UML version 2, the notation became cleaner. Here, we still see the same logical separation. User interface components like seminar management interacting with infrastructure components. But the visual language is more standardized to show how modules are required or provided through specific ports. A critical rule in architecture is to avoid dependency cycles. In a clean client-server subsystem, the server does not depend on the client, meaning changes to the client's interface don't break the server. However, in a peer relationship, each subsystem depends on the other. This creates a cycle where a change in subsystem C forces a change in D, which might then force another change back in C. This is the definition of tight coupling, and we want to avoid it. To organize these dependencies, we use architectural patterns. We've discussed the three-layer architecture before, where we group things into presentation, application logic, and storage layers. Using UML packages here allows us to see how application windows in the presentation layer might depend on control objects, which in turn utilize business objects. Classic examples of layered systems include operating systems and communication protocols. These systems are designed to support increasing levels of abstraction. A kernel sits at the center, surrounded by utilities, which are then used by the application layer. This supports enhancement and reuse because you can define standard interfaces for each layer. The main disadvantage is that in complex modern systems, it can be very difficult to identify perfectly clean layers. When designing layers, you must choose between open or closed architecture. In a closed architecture, a layer can only use the service of the layer immediately below it. This minimizes dependencies and reduces the impact of change. In an open architecture, a layer can access any lower layer. This results in more compact code and better performance since you can access services directly, but it breaks encapsulation and increases the complexity of dependencies. The number of layers depends on the system's complexity. A two-layer system is a simple client-server model. A three-layer system separates out business logic, which makes the UI and database layers easy to modify. Four-layer system goes further by separating application logic from domain logic. We can even have partitioned four-layer systems to identify entirely separate applications sharing the same domain and database. And filter style is common in Unix shell scripts and compilers. In a compiler, lexical analysis leads to parsing, then semantic analysis, and finally code generation. The beauty of this style is that filters are independent. They don't need to know what they are connected to. This allows for parallel implementation and specialized analysis, such as checking for deadlocks or calculating system throughput. In object-oriented styles, we decompose the system into a set of interacting agents. This promotes data hiding, as the internal representation of an object isn't visible to its clients. However, a major disadvantage is that objects must explicitly know the identity of the other objects they wish to interact with, which can lead to complex webs of dependencies. To solve the identity problem, we use event-based or implicit invocation styles, or what we often call publish, subscribe today. This is used in GUIs, database triggers, and debugging systems. Here, the announcer of an event doesn't need to know who will handle it. This makes it incredibly easy to evolve a system by adding new agents. The trade-off is that the components lose control over the exact ordering of computations. Repository architectures like central databases or Blackboard expert systems revolve around a shared data store. This reduces the need to duplicate complex data across different agents. You can choose to put control in the agents, the Blackboard, or both. The primary risk here is that the central repository can become a performance bottleneck. One of the most famous patterns is the Model View Controller, or the MVC. You have one central model and many views. Each view has an associated controller to handle user updates. When the model changes, those changes are automatically propagated to all views, ensuring the user interface stays in sync with the underlying data. In summary, the goal of good architecture is to avoid unnecessary coupling and maximize cohesion. Whether you use a layered approach or a pattern like MVC, the goal is to modularize for reusability with well-defined public interfaces. While we use UML diagrams to discuss these structures, remember that perfect adherence to UML syntax isn't the point. Clearly communicating the architecture to your team is.